We've evaluated induced sign characters at Cauchy-Lustig basis elements of the symmetric group algebra. Now let's evaluate their Q analogs at Cauchy-Lustig basis elements of the Hickey algebra. So recall that we have if we want to evaluate the induced sign character indexed by lambda at a Cauchy-Lustig basis element of the symmetric group algebra, that this is the number of column strict P of FW tableau of shape lambda transpose. Oh, this only works if W avoids the patterns 3, 4, 1, 2, 4, 2, 3, 1. No general combinatorial interpretation is known for all W. And FW is the zigzag network associated to W. P of FW is its path poset. Now if we switch to the Hickey algebra, we have the similar evaluation being a polynomial in Q with non-negative integer coefficients. This specializes at Q equals 1 to the evaluation above, which ends up being an integer. To interpret the coefficients of the Hickey algebra evaluation, we're going to use inversions in P tableau. So given a poset P and a P tableau T, that is a Young diagram filled with poset elements, define an inversion in T to be a pair IJ with I less than j as integers, I incomparable to j in P, and j appearing in an earlier column than I. So a little bit like an inversion in a permutation, except that as poset elements, these have to be incomparable. They don't have to be in the same row either. Just the greater index has to appear in an earlier column. So the interpretation of the Hecke algebra evaluation for W avoiding 3, 4, 1, 2 and 4, 2, 3, 1, we have that this evaluation equals the sum over column strict tableau T the sum over all the column strict tableau of shape lambda transpose Q to the number of inversions in that tableau. So for example, let's compute epsilon 221 Q of the Kaiserstein-Lustig basis element indexed by 34521. So we did this for Q equals 1 before. So the planar network for W looks like this. And if we look carefully at the paths and the posts that they form, then the post set looks like this. And we're going to sum over column strict tableau of shape 3, 2. So we noted before that they are 1, 4 in a column, 2, 5 in a column 3, or 2, 5 in the first column, 1, 4 in the second column, and 3 by itself. Those are the only two possibilities. Now we have to count inversions in these and assign each one Q to the number of inversions. So we're looking for larger letters that are followed by smaller letters. Not necessarily in the same row, but in the smaller letter in a later column. For instance, 4 is greater than 3 as integers. 4 and 3 are incomparable. So 4, 3 counts as an inversion. And then 5 is greater than 3. 5 and 3 are incomparable. 5 appears in an earlier column than 3. And I think those are all the pairs of greater number followed by smaller number. So the contribution of this tableau is Q squared. Then here we have 4 and 3 and 5, 3 again. Now we have 5 and 4. 5 and 4 are incomparable. 5 appears in an earlier column. Two and 1. 2 is greater than 1 as integers, and they're incomparable in the post set. Oh wait. Okay. 5 is bigger than 4. So we have a contribution of Q to the 4th here. and I see that I missed one over here. We have 4 and 2. 4 and 2 are incomparable in the post set. 4 is greater than 2 as an integer. So there's actually 3 inversions in this tableau. So that means that epsilon 221 of the Kazhdan-Luttig basis element indexed by 3, 4, 5, 1, 2 equals q cubed plus q to the 4th. We can see that if we plug in q equals 1, we get 1 plus 1, which is 2. So every tableau is going to contribute a power of q, which is good because when q equals 1, every tableau should be contributing exactly 1. Now the proof is a little bit tedious, I think, to do all the details, so let me just give you an idea. It involves immanence. It involves the quantum version of immanence that live in the quantum matrix by algebra A and Q. So the variables x are not commuting anymore. So we have relations like xkl xij equals xij xkl plus root q minus 1 over root q xil x kj if k is greater than I and L is greater than j. So we have relations like that, etc. Now if we multiply out the expression for the immanent, remember this is a sum. It looks exactly like the q equals 1 expression, except that our determinants of submatrices are quantum determinants. So if we multiply that out and we put the monomials in lexicographic order, we obtain powers of q. Actually, q to the 1/2. Then when we write this as q to a power, well, root q to a power, so we'll take out those powers of root q. So we'll get a polynomial in q times this power of root q, which is sort of on the side. So this is just integer powers of q. And then we evaluate this at the path matrix of FW the path matrix A of FW So by evaluate, I mean xij is going to be set equal to aij. Then you can show with a couple other lemmas that this ends up giving us precisely q to the number of inversions of t for each column strict P of FW tableau T. So we're drawing exactly the same pictures, the column strict tableau, and we're just associating a power of Q to each one now. The end.